actually interacting. The forces are what are called Newton's third law pairs, where when an object interacts, one force is the equal but opposite of its counterpart. All right, that is one type of interaction. But a second type of interaction doesn't deal with forces per se, but it just deals with the fact that the objects are connected together. And if the objects are connected together, then they have to be moving as a single unit. And so their accelerations become the same. If objects are connected, they have what is called the acceleration constraint. And so we did an example with that. And so let's continue from here. Now for objects interacting, we looked at objects with ropes as well as pulleys. And we're going to go one level deeper into both. So let's dig a little bit deeper into ropes first. Ropes. So I'm sure you will agree with this observational note that many objects are connected by string / rope. Because this is such a common occurrence, of course, understanding it in a slightly deeper fashion should be of great value to you guys. In terms of how we are concerned with, ropes apply a force that we call tension. It is called tension, and we give it the notation capital T. So let's do a simple thought experiment. Consider crates A and B connected by rope. And they are accelerating in the x direction. So we have object A, and we have another object called B, and here we have a rope that connects. And let's say there is some F net on object B such that the entire system is moving this way. So B is pulling all the objects together. With this in mind, I have a question for you guys. Is the magnitude of the tension of the rope onto A, is it greater than, less than, or equal to the tension of the rope onto B? Or alternatively said, we can flip the subscript around. Is the tension of A onto the rope, is that greater, less than, or equal to the tension of B onto the rope? Actually, let's ask it in this fashion. So essentially, we want to know at these junction points, tension, this is B onto the rope, this is A onto the rope. Do they have equal tensions? Or is one greater than the other? And if so, then which one is actually greater? So let's fully hash out this idea. So here's one thing that we know. That the net force of B is in the positive x direction. So we could, and that's going to be our starting point. Since F net on V is greater than 0, we know something about object B. From Newton's second law, what can we infer? If the net force on B is greater than 0, what does Newton's second law tell us?
It's accelerating.
Yeah, acceleration of object B has to be greater than 0. Right, Newton's second law is F is equal to ma. So if the force is greater than 0, then the acceleration has to be greater than 0 as well. We also know, by the fact that all these three objects are connected, that the acceleration of B has to equal the acceleration of A, which is also equal to the acceleration of the rope. Meaning all of these are greater than or equal to 0. And this is by the acceleration constraint. Now, notice here, the acceleration of the rope is equal to 0. If this is true, then from Newton's second law, then we know that the net force on the rope has to be greater than 0. Everyone follows so far? So then let's do the force balance on the rope. What is actually the net force on the rope? We have object B pulling it to the positive x-axis. So then the net force of the rope is positive tension of B onto R. And we have object A trying to pull it backwards, minus tension of A onto R. But we just discussed that the net force on the rope has to be greater than 0. Meaning, from here we can conclude that the tension of B onto the rope then has to be greater than the tension of A onto the rope. Right, all we did was we just moved this, move this over here. So what does this tell us? This tells us that the tension here is much greater than the tension here. Now, is that intuitive? Really? Oh, you're nodding? Okay, for me, I don't think so. Because it seems like the tension should be same here and here. It should actually be the same throughout the entirety of the rope. So then what is going on? This is counterintuitive, but let's actually think about everything in a realistic fashion. Object A is the one that's moving this way, and it's pulling how many objects? No, 2. Rope and the object A. Right? So at this point, it's pulling the entirety of the rope as well as all of object A. Whereas over here, at this junction, what is this pulling? Just object A. That's why the tension is higher here. It's including the mass of the rope. It's pulling 2 different objects, so it's hauling the rope and object A. That's why it's greater. So TBR is greater than TAR because TBR is pulling rope and object A. Whereas TAR is only pulling A. Now, what the expected result would have been that TAR would equal, we expected the TBR to equal TAR. We expected the two tensions to be identical. Yeah, question.
I'm confused. Wouldn't A also be pulling the rope because of equal and opposite reaction?
Wouldn't A be pulling? Right. But what direction is the entire system moving?
In the positive X direction?
So yes, it is pulling it, and that's why we had minus TAR on the rope. So if we do a free body diagram of the rope, okay, just in the X direction, this is TBR, and that is TAR. And yes, it's pulling on the rope, and that's why it's there. Does that answer it or no?
The talk after.
Okay. But we expected the tensions to be equal because of Newton's third law. So how come that wasn't the result? Let's do the more full derivation. F net in R is going to be positive TBR minus TAR. Right, that's these two acting. So one is pulling in the positive X direction, the other one's pulling it back into the negative. But Newton's second law tells us that this is equal to the mass of the rope times the acceleration of the rope. This is Newton's second law. TAR and TBR are equal as long as this right-hand side is equal to 0. So here, TBR will equal TAR as long as either the mass of the rope is equal to 0 or the acceleration of the rope is equal to 0. And take my word for it, the fact that the two different tensions are uneven is going to lead to a lot of complications in the problem. It's going to make the problem unnecessarily complex. Instead, ropes tend to be very, very small or light or much less weight than the object that they're intended to actually pull or push, right? Therefore, right here, mass of the rope is going to equal 0. We use this as an approximation. So we use what is called the massless rope approximation. Ropes are intended to be light, right? They're trying to make it easier to carry things. That's why it's meant to be light. And so we have what is called the massless rope approximation, which states that the mass of rope is approximately equal to 0, at which point the tensions are all the same. So TBR is equal to TAR essentially, or in general, tension in rope is constant. The tensions also become Newton's third law pair. So they end up being equal and opposite in direction. So when we look at this free body diagram of the rope, notice, well, I didn't draw it in a good fashion, but this is equal but opposite of that, right? These are considered to be opposite pairs, Newton's third law pairs. So one of the effects that happens with the massless rope approximation is can neglect rope as an object in system, meaning no need to draw free body diagram. No need to draw the free body diagram. In the problem set, you're, I believe, going to do a problem where you cannot use the massless rope approximation, and you'll see exactly how negligible it is, but you'll see how much harder the problem was to do. And so there is a trade-off that is often done. If it makes your life 90% easier at the cost of 1% accuracy, yes, it's definitely worth it. Right? Definitely worth it, and that's this massless rope approximation. So those are ropes. So that's one of the ways that objects can interact with each other is through tension, is through ropes connecting different objects together. Another one, which we briefly discussed, was this idea of pulleys. Pulleys. So pulleys look like this. We'll put a P for a pulley. Now let's draw the free body diagram of objects A and B. Object A, you're going to have force of gravity on A, the normal force on A. Tension of B onto A. And some aspect of friction on A. On object B, you have force of gravity on B. And you have tension of A onto B. Now here, we're already invoking the massless rope approximation. Therefore, these tensions become Newton's third law pairs. We must remember to actually connect them. But one thing you're going to notice, Newton's third law says for every action you have a what? Equal and opposite reaction. Meaning, if a force is this way, the opposite force has to be this way. But look at these two interaction pairs. One is going this way, but one is going that way. Do you see that? So it's not equal and opposite, it's equal in a different direction. This is what the pulley allows the system to do. So pulleys allows a change of direction for quote unquote free. So these are still Newton's third law of pairs, even though they're not equal and opposite, because we have a pulley. However, there is a built-in assumption. Now, in the most recent lab you did, which was still 2 weeks ago, you guys used a pulley on the force table. Do you guys remember that? The pulley systems? Pulleys work by there being like a spin wheel where a rope is latched onto it. The pulleys are meant to have very, very low friction, but it still does have friction. So it is only free as long as you have a frictionless pulley. Frictionless and massless pulley. As long as you have a frictionless and massless pulley, then you can change directions of tension for free. So then, can change direction of tension for free. This is why ropes and pulleys are so commonly used. Oftentimes, we have a tremendous source of force that we have constant access to, and that's called gravity. Gravity. Now, we can use that to lift other things by using pulleys that look like this. If one object is heavier, then you can lift the other object, and you can do that as soon as you connect them through a rope and a pulley. And so this allows you to take advantage of one of the benefits that gravity provides for you, which is a immediate access to force. As long as you have a rope and a system of pulleys that can actually withstand the force of gravity, then you can do different things for whatever your purposes are. So very useful stuff. Now let's do two examples going over some of the topics that we've discussed up to this point. So let's say we have this scenario, we have objects A and B, where massive A is greater than massive B, and let's say these boxes were both moving in that direction. But, and this will be your hand, okay, your hand. Your hand is going to be slowing the boxes down. So we have, let's say, box A and B are sliding to the right. Across a frictionless table. Hand is slowing them down. And the question you're tasked with is the following. I want you to rank in order of force, where the options are F, hand onto object, or hand onto B, force of B onto the hand, force of A onto B and the force of B onto A. Alright, I'll let you guys think about it for a minute while I grab a drink of water. Right back. Any guesses?
Will the force of A still be the greatest because it's pushing both A or B in the hand because it's slowing down, not stop?
Are you sure A is slowing down, or A is pushing both B and the hand?
No.
You're kind of correct, but kind of not. So I see where you're coming from, but the scenario is slightly different than what you expected. Primarily, you're thinking your reasoning would be right if the acceleration was towards the right. The objects here are accelerating in which direction? Yeah, it's this direction. They're moving this way, but slowing down, meaning it's accelerating to the right this way. So, instead of A pushing on B and the hand, it's actually the hand pushing on B and the A. So, in this scenario, this is going to be the correct sequencing. FBH is equal to FHB, which is greater than FAB, which is equal to FBA. And this is because the hand is slowing down both B and the A, whereas B is only slowing down the A. So there is greater force because the hand is slowing down two objects, whereas B is only slowing down one object. Right, so essentially, correct rationale you had, it's just you have the acceleration going in the opposite direction. So, since H is slowing objects down, A is equal to negative AX. In the I. Meaning, if we do a analysis on object B, we would get the following. The net force on B is going to be negative mass times acceleration in the x direction. And on object B, we have the following. This is going to be force of A onto B. This is going to be force of the hand onto the B. So we have positive FAB minus FBH. From here, we can arrange to get that FBH is going to be FAB plus the mass times the acceleration in the x direction. And so here, we can see very, very clearly that the force of the box onto the hand is equal to A on the box plus mass times however it's accelerating. Sorry, this is mass of B times the acceleration. And so here, when we did the full analysis, we not only showed that FBH is greater than FAB, but we know by exactly how much. And it depends on how quickly the system is accelerating. And of course, we would use Newton's third law for completion. FBH, the magnitude is equal to FHB, and FAB is equal to FBA in terms of the magnitude. So they are equal in magnitude but opposite in direction, but we cared about just the magnitude. And so that's how we would arrive at this ranking. Now question.
And then just to double check, the reason why the force of BH is greater than the force of AB is just because it's accelerating in the negative direction.
Yeah, the hand is the one that's slowing it down, slowing both of them down.
Okay, cool. Just double check.
So you can also think of it as, let's say, if you have two siblings, let's say you're holding your little sibling, but then your little sibling is holding your littler sibling. Who's holding more? Who's holding more weight? Right, you are, because you're holding two different people.
Yeah.
Let's do a slightly difficult or more difficult example. So let's say, this time we're actually going to be using pulleys. A and B. Let's say B is 100 kilograms and A is 200 kilograms. That's the only information you're given. And you want to know what is the acceleration of it? And many of you guys are going to think, not enough information. Because it seems like we are definitely not given enough. Now, unfortunately, we do have enough information, so let's actually look at the solution. So as with all dynamics problems, we want to know what the free body diagram looks like. We want to know all the different forces acting on the system. Now, just because it looks like there's not enough information doesn't mean that it actually is, you actually do have too few. That will only come to light with a deeper analysis. So over object B, the free body diagram looks like the following. Force of gravity down, tension of A onto B up. On object A, we would have force of gravity on A down and tension of B onto A up. And the two different tensions would be third law pairs. And when we do this, what did we approximate or what did we assume? By equating this, we assumed massless rope as well as frictionless and massless pulley. Yeah, question.
I'm assuming that's going to be explicitly mentioned in the problem. That's
No, okay. Yeah, actually, I forgot to mention. Pretty much, you can always assume these unless I tell you you can't. So like in one of the problems, I actually just tell you, assume rope has this mass, then do the calculation. And then if you say assume mass of the rope or rope is massless, then it's going to be an automatic 0. Because like I told you, it's not massless. But the problems are going to get extremely, extremely difficult unless you have this. Right? And right now, you don't know how to even, okay, with a massless rope, okay, when there's actual mass, you guys technically do know how to solve for it. And that's why I'm going to give you one of the problems to do in the problem set. But it just becomes much more difficult, and you barely get like a percentage closer to the actual correct answer. Right now, we haven't discussed how to even take these into consideration. By the end of the semester, you will. By the end of the semester, you will. So here, that's the free body diagram. But we also know something else. One of the things that ropes do is that it connects different objects together, meaning we know something about their accelerations. What do we know about their accelerations? Yeah.
Going back to the everything is greater than 0, or is that no?
Well, yeah, they will be accelerating, but I'm looking for a little bit more specific. Yeah.
The acceleration of A is going to be negative y.
Yes, the
B is
acceleration
positive y.
of B in the y direction. Right, B as 1 goes up, so as B goes up, what does A have to be doing? It's going down. That's how pulleys and ropes work. And so as ABY goes up, we know this is going to be the acceleration of A in the y direction except negative. They are inversely related. As one goes up, the other one goes down. So we know this to be true about the accelerations. So the free body diagrams and the acceleration constraint, these are both what the problem is simply informing us without actually telling us. Okay? This is just from our analysis, and we got a lot of information simply by considering the different forces and their interactions. Then we can actually look at analyzing the information that we accrued. So let's look at Newton's second law. So on A, and here I think on the free body diagram it's very clear. The interesting physics are in the y direction. We don't have to consider the x direction at all. So second law, we'll just say in y. So on object A, we have the net force on A is going to be positive tension B onto A minus the force of gravity onto A. And the second law is going to tell us that this is equal to mass of A times the acceleration of A. In contrast, on B, we have the net force on B is equal to positive TAB. Tension is trying to pull B up, minus force of gravity on object B. Force of gravity is pulling it down. This is equal to the mass of object B times the acceleration of object B. Now we wanted to know what is the acceleration in the A direction. Or sorry, not in the A direction. What is the acceleration of object A? So we wanted this parameter. Well, let's look at all the, so this is where our analysis has been reduced to. We just need to look and assess, do we know each and every single parameter? So do we know the tension? We don't know what this tension value is. Do we know the force of gravity? Well, we have the mass, so we do, so we know the different forces. Right? Likewise, we know these masses. We don't know this tension. Do we know the acceleration of A? No, we don't. Do we know the acceleration of B? No, we don't as well. So we have 4 unknowns, except the acceleration of B, we have a relationship to A. So in actuality, okay, well, we have this too, but let me also do another thing. We also forgot to take into consideration the 2 different tensions are Newton's third law pairs, meaning that their magnitudes are the same. We also have TAB is equal to TBA, and let's just call it a generic tension T. With this in mind, this expression becomes, or these 2 equations, T minus FGA is equal to massive A times the acceleration of A. Also, we get T minus FGB is equal to massive B times, now we applied the acceleration constraint, that the acceleration of A is negative, or sorry, acceleration of B is negative of acceleration of A. Now let's reassess. We don't know tension. We do know forces of gravity, we do know the masses, and we don't know the acceleration of A. Now we got it down to 2 equations and 2 unknowns. Because we have enough equations to match our unknowns, this becomes a system of equations problem. And you can use whatever technique you like. In this example, I'm just going to, I can see that I can get rid of a t by subtracting the second equation from the first one. So I'm going to do the first equation minus the second equation. At which point, the 2 different tensions cross out, and we get negative force of gravity of A minus a negative force of gravity on B. This is going to equal mass of A times the acceleration of A minus mass of B times the negative acceleration of A. And now it's just a matter of simplifying. We get FGB minus FGA is equal to the acceleration of A times mass of A plus mass of B. Whereas the force of gravities, these are simply mg. So this would be mass of B times G minus mass of A times G is equal to acceleration of A, ma plus mb. On the left-hand side, we could factor out a G. mb over mb minus ma is equal to acceleration of A times ma plus mb. Meaning that the acceleration of A is going to be our gravitational constant G times mass of B minus mass of A divided by mass of B plus A. And this is our final solution. Of course, for us, we can't just keep it algebraic, although that's what I would like to do, but we were given numbers. So this is going to be G times 100 kilograms minus 200 kilograms divided by 100 kilograms plus 200 kilograms. Essentially, this is equal to negative G over 3. Where if you plug in G as negative 9.8, you get negative 3.27 meters per second squared. And that is the final answer. So, from having this pretty much seemingly what appears to be not enough information to answer this question, after a little bit of analysis, free body diagram, acceleration constraints, and it turns out you're actually were given plenty of information, enough to solve it, no problem. But let's think about how, if we did everything correctly. If we just look at this pulley, which one is heavier? A is heavier, so A will likely win, and it's going to go down. Is that correct? It's going to go down. So the acceleration of A, because it's going down, which should be a negative number, and it is. And so that should give us confidence that we did the problem correctly. Also, how to understand this expression. So our solution is actually G MB minus MA over MB plus MA. Now, how to understand this numerator is the following. A beats B by how much mass? By 100 mass. That's how much A beats by. So the gravitational pull on this entire system is going to be 200, or it's going to be the difference, and that's what's up here. But that net gravitational pull is now moving how many objects? A and B, which weighs a total of 300 kilograms, and that's down here. So in a pulley, you have two competing forces. The net force goes up on the numerator, and the overall, mass that the force is going to move, that shows up on the denominator. And of course, it's dominated by, or dictated by, the gravitational constant. So that's how to understand this idea of a pulley.
Sorry, Louise. Could you please go back to the final answer just really quick? Thank you.
All right, and this concludes dynamics in one dimension. Meaning, what's coming next? Yeah, dynamics in 2 dimensions. So this was the easy stuff. No, I don't think the complexity actually increases when we go into 2 dimensions. So next we are going dynamics in 3 dimensions. The complexity doesn't actually increase too much. The only thing that we have to remember is Newton's second law and exactly how that's going to be modified when we consider a second direction. Newton's second law simply tells us that the net force is mass times acceleration in its vector form. This looks like a single equation. However, we have to remember that this is true for each dimension. And so in 2 dimensions, this single equation is actually a combination of two. It's F net in the x direction is mass times the acceleration in the x direction, as well as F net in the y is going to be mass times acceleration in the y. So essentially, dynamics in 2D is essentially dynamics in 1D, and you do it twice, just for different directions. Now, if the x and y components are independent, then solution is straightforward. Else, we do not have enough math. But for our case, this is going to be a great, pretty much, we're going to, at least quantitatively speaking, limit ourselves to this constraint. So in 2D, when we were at least in the kinematics sections, we looked at a few different types of motion. One was projectile motion. The other was, I kind of heard it whisper. What is it? Circular motion, yeah. So we're going to be looking at both of those. So projectile motion, very, very simple. From kinematics, we had the acceleration in the x direction is equal to 0. Acceleration in the y is negative g. All right, these are what characterize projectile motion. But now we can answer the question why. Before, I just told you these were true, but now we can actually do the analysis. When an object is in projectile motion, so let's say it's going to be following this trajectory, but let's say the object is right here, what are all the forces acting on this system? What does our free body diagram look like? You have force of gravity, what else? Trick question, that's it. Right, that's all we have. Except that's not a trick question. There's no trick question. Meaning, the net force in the x direction, according to Newton's second law, is mass times acceleration. Now the force balance will tell us that there's only one force acting on it. That would be the force of gravity in the x direction. But what is the force of gravity in the x direction, or the x component of the force of gravity? 0. Therefore, we know that the acceleration has to be equal to 0 in the x direction. We could do the similar analysis in the y. Second law tells us that the net force has to equal mass times the acceleration in the y. But what is the only force acting in the y? Which is equal to force of gravity, negative force of gravity in the y direction, which is equal to negative mg. And putting both of these together, tells you that the masses cancel out and the acceleration in the y direction is negative g. And this is where Galileo got his fame. And I'm sure there's many people that came to this conclusion as well. But Aristotle's thought was the predominant thought that lasted many, many eons. and he thought that heavier objects fell faster to the ground. Wait, makes sense? Alright. Well, yeah, but it doesn't, because of this analysis here, and Galileo made that observation. And it's because the force of gravity and Newton's second law, they both have a mass term, which ends up canceling, and the acceleration is purely determined by the gravitational constant g. But this is without drag. Let's consider the scenario with drag to let me convince you how difficult drag is. I've been telling you and warning you, drag is very, very difficult. You don't even have to write this down, by the way. Projectile motion, acceleration is 0 in the x, in the y is negative g. Very, very simple. With drag, with the model that I showed you, this is what the acceleration values will look like. In the x, it is equal to negative rho, that's the density of the fluid, times c, the drag coefficient, times the a, which is a cross-sectional area, divided by 2 times the mass, times the x component of the velocity, times the square root of the x component of the velocity squared, times the y component of the velocity squared. All right, which one's simpler, 0 or that? Right, it's clearly 0. In the y direction, it's negative g minus that entire thing with a minor change, which is that it's vy square root of vx squared plus vy squared. And here's the thing, just using these equations shouldn't be too difficult. But it's arriving at these equations, yeah, do you think arriving at this was difficult? Okay. Right, imagine trying to arrive at this guy. But this is where differential equations comes into play. But you're not expected to know it. Like I said, this is why we neglect drag. At least quantitatively. There is an aspect of drag that I expect you guys to know, and that's on the qualitative idea. So this is where you should start writing down again. So this is without drag. Without drag, now if we were to draw our trajectory, this is now taking one of the midterm questions. To go the maximum distance, you want to launch it at 45 degrees. And when you deviate equally from 45 degrees, either lower or higher, so let's say we deviate by 15. So this will be 30 degrees. Or we deviate higher, which is 60 degrees. You're going to land at the same location. So 45 is the maximum distance you can get. And as you deviate equally from 45, either higher than 45 or below 45, you will land at the same location. This is without drag. With drag, the scenario changes a little bit. With drag, do you guys think 45 degrees will still be the maximum distance you can get? Raise your hand for yes. Raise your hand for no. Okay, those who answered no, do you think it'll be higher than 45 or less than 45 degrees? Who says higher than 45, raise your hand. Who says less than 45, raise your hand. Okay, who's confident about their answer? So it is not at 45 degrees. Because how drag affects it, the longer you're in the air, the more drag will have an impact. So the trajectory is no longer parabolic. It's going to look kind of like a trajectory that you would imagine a frisbee to have. It starts off kind of parabolic, but then it gets truncated because drag kind of takes over. So it looks like this. If this is 45 degrees, if you throw it slightly lower, you will surpass that 45-degree mark. But how much lower ultimately depends on some of these parameters. So this will have to be 45 minus some angle theta. Now, if you were to throw it higher than 45 degrees by the same amount of theta, do you guys think it will go higher or lower, or further or lower, or wait, further or closer than the 45-degree mark? Why closer?
Yep.
So that's correct. It'll do something that looks kind of like this. Well, it'll be closer because it's in the air longer. Remember, the longer you're in the air, the more drag will impact your movement. So here, max is not 45 degrees. All right, well, this is pretty much where I got to in the calc-based section. So we can end it here. Although, yeah. I'll see you guys Wednesday. Wait, once again, you don't have to know this aspect about drag. You will not have to compute numbers, but these qualitative features about drag is fair game for quizzes and exams.
So what distance that the object falls when you throw it at an angle of 45 plus theta and 45 minus theta, will they vary around 45 by the same amount?
I don't think so. I think that is determined by some of these parameters. That might be interesting.